Swayam Prabha. Digital India. Educated India.
Okay, so the welcome back. I think I'm intend to finish this stress-strain relationship today, and let's see, we may go a little beyond also. Now, up until yesterday, we have talked about three methods by which we can collapse 3D to 2D. But you should be always remembering this, that the results will not be compromised by doing this. Whatever the result you will get in 3D, you will get in 2D also. Now, if you remember, one time I told you there is some anisotropy. See, one is isotropy. So far we have discussed isotropic. And isotropic behavior, we have said the modulus of elasticity and Poisson's ratio, these are same in all direction, okay? Equal in all direction, or same in all direction. Okay, now if in one direction it is not the same, then what happens? So that thing we call transverse isotropy, and there is something called completely anisotropy also. I will come to that. Now, what is transverse isotropy? And this is somehow related to definitely in mining or in geotechnical engineering. This is very important. Let me give you the example where it is. Now, mostly our coal deposits or a sedimentary rock, if I have to put it in X, Y and Z plane, they normally deposited layer by layer. So let's say this is one layer, then on top of that I may use another color, on top of that another layer, and so on. So on top of that this. So this may be coal, this may be sandstone, on top of that may be a shale layer, then again coal, it can be anything. So this is a material 1 and this is material 2. There are two different material. Because it is deposited layer by layer, this is what is the sedimentary formation is all about. I think in your geology class, they are going to explain it to you. So they have different material type, meaning they have different E, let's say if this is some E2, mu2, this will be also E1, mu1, something different. Okay, the elastic property, strength properties, all will be different because the rock type is different. Okay. Now, under this situation, how we are going to analyze, let's say, the stress-strain behavior of this material 1. Now, what is happening is, as you're seeing, because the deposition direction, it has deposited in this direction. So if I now take a core sample, from this direction, so I am taking core sample from this direction, that means that cylindrical sample I am cutting it or drilling it, and if I take in this direction, okay, this is the depositional direction, mind that. So if I take in this 3 direction, and then if I take it, somebody has to mute your mic. So if I now test these 3 samples and find out E and mu, we will see more or less we will see somebody has to mute your,
Santosh Kumar, could you please unmute yourself?
please mute. So you will see these two directions, what we call the plane of isotropy. This plane of isotropy, you will get one type of modulus and Poisson's ratio. Let's say U1, mu1. But in this direction, the depositional direction, when we will test, then we will get some other. Okay? And how they are deposited and how the water is squeezed out and all these things will be told to you in your geology class. So there will be distinct perpendicular to the plane of isotropy. That's why it's called transverse. The perpendicular direction to the plane of isotropy. The properties are different and significantly different. Okay. And that's why it is called transverse isotropy. And this is very much prominent in the rock type we normally test. Okay. So in this case, your C matrix, now I'm going to write your C matrix. In this case, the C matrix, you remember that compliance matrix I told you, it is written like 1 minus mu1 minus mu2. So I am assuming X and Y are plane of isotropy. Okay, X and Y are plane of isotropy. So 1 mu1 and this is in the Z. So that's why it is mu2 0 0 0. That remains as it is. Minus mu1 1 minus mu2 0 0 0 minus mu2 this is E1 by E2 0 0 0. Same, it will be 0, these three zeros, and here it will be 2 into 1 plus mu1 0 0 0. This we normally call, I will explain what is G2, and this is 0 E1 by G2. This becomes my that C matrix. Now what is G2 if you ask me? This G2 is nothing but it is given as E1 E2 by E1 plus 1 plus 2 mu2. Okay. This is the shear modulus, you may say, in the depositional direction. Okay. So you can see the matrix has changed. Now we have not two properties, not only E and mu, we have now four properties. E1 mu1, U2 mu2. Okay, the four properties. Two are along the plane of isotropy, and that's what we are assuming, that in the X and Y direction they are same, and in Z direction, transverse to the plane of isotropy, they are different. Okay, so the C matrix will now change like this. Now in the book it is given, if you reverse, you can also make D as a C inverse, and this is little big matrix, so I am not writing it, or you can get it in any standard literature. In the book also it is given. So my point is, if there are in one particular direction properties are different and two other direction they are same, we call it transverse isotropy, and since they are linearly behaving, we call it linear transverse isotropy. Okay, this is the definition right now you have to know. Okay, then we go to pure anisotropy. If I have to define, then there are some empirical equations are given. You know the difference between analytical and empirical. Analytical is which you can derive, like so far we are doing. All these are analytical. We are deriving from the basic principle of mechanics or the law of solid and all this. Some are from the experiments, it has been revealed that the relationship exists like this. So those are called empirical equations. So one empirical equations on anisotropy is given for rock type material only. Is something like by a parameter called n. You can just write it down. 2k plus m. Okay, the author who has given, he has found out from some experimental studies with semi-analytical and semi-empirical. He has given a parameter n can represent the anisotropy, and it is given like this. Now what is k? He has given k is equals to similarly this is E1 by E2 minus mu2 square by 1 minus mu1 square, and here said m you write it E1 by G1 minus 2 mu2 1 plus mu1 by 1 minus mu1 square. Now here G1 is same E1 by 2 into 1 plus mu1. That remains, that is the shear modulus. And this mu2 and E2 are again in the transverse direction. Okay. Now the question becomes, what he has given is the value of n by which we can now say whether it is anisotropy or isotropy. What he has said, if this value of n is less than 2.1, then you call it quasi isotropy, meaning it is basically isotropy if it is less than 2.1. If n is somewhere in between 2.1 to 2.5, then we will call it poor anisotropy. Okay, and if it is between 2.5 to somewhere between 3, then we will call it moderate anisotropy, and if it is greater than 3.0, this is definitely very strong anisotropy. Okay.
Sir, but in the condition for quasi-isotropy is given that n should be less than 5.1.
Oh, no, you correct. There is a typo mistake. You correct this thing.
Yes, sir.
Okay.
Okay, sir.
Okay. Okay. Now, can you tell me the value of n for isotropy? Pure isotropy. Value of n for pure isotropy. Quickly, anybody? What will be the value of k?
0.
K is 0. Oh. See, E1 equals to E2, isn't it? So K will become 1. And mu1 equals to mu2. So K become 1. And M becomes 2. If you just do, if you calculate, m will become 2 for pure isotropy, and then n become 2. So pure isotropy, it is basically 2. And then he has given this classification here, and this classification, it says that below 2.1 is basically quasi-isotope. So what we can do here, if we have the data, like testing data, E1, mu1 and E2, mu2, so we can quickly put in that equation, n equation, and we find out whether it is basically whether within this n value. I normally also assume up to 4 anisotropy I consider as a isotropy. So if it is less than 2.5, then pretty much whatever the isotropy equations we can directly use. And if it is going below 2.5 or above 2.5, then we have to use that transverse isotropy, that equation. Okay, we cannot no longer assume that this is true in all directions, so we can change it. Only the C matrix or D matrix will change. Okay, so far clear? But this need to be established after testing in the laboratory. You just cannot arbitrarily say a rock is isotropy or anisotropy. You have to test it, then only you will know. So testing is very important. Now I will go to I think probably the last topic in this chapter, which is little bit I am going to touch upon that, which is called plasticity. This plasticity will not be talked too much into this class, but when you will come to in your third year, and there will be another subject called ARE, Applied Rock Engineering. There the application of plasticity may be told to you. Okay, but let me ask you something. What is the meaning of plastic? Like elastic, you can define. Now, what is the meaning of plastic? Does anybody know this word, the meaning of the plastic? See, one is elastic material, we know all. So far we are discussing only that. Now, what could be the plastic material? Like you know the plastic bottle, Thumbs Up, Coca-Cola come in a plastic bottle. Do you think that material which is made, they have elasticity? That means they have E and mu, those materials. We call them plastic bottles.
Some materials.
Bolo.
So that materials that can be deformed easily. That
is called plastic. Okay. So this plastic bottle, do they have E and mu? If I test, will they have modulus of elasticity and Poisson's ratio?
Yes.
They will. So they are also elastic, that means. Because those are elastic properties.
Up to a certain limit.
So always remember that every material is elastic material until certain load, certain stress. So if you remember, initially I have plotted even in one dimension the stress versus strain. So I told you initially this is Hooke's law, and then it either falls like this or abruptly falls like that, or it goes like this, or as a theoretical thing, it is straight line. I told you this is strain hardening. We call strain softening. This we call brittle. This is also called ductile, okay? And this is what we call the perfectly plastic material. But you see, until this, from here to here, it is still elastic. That means with load, with stress, the strain also increases according to Hooke's law, more or less straight line. And then here it becomes the plastic material. So each material will have certain range where they will behave in elasticity. Okay? That's why even a plastic material will have elasticity. Okay? Do not be confused. Okay? They will have some E and mu. Okay? Whatever may be the value. Okay? But they will have. Value means this may be, I can draw, this may be something like this, very, slanted curve, but they will have certain E and certain mu. Okay. So this is what elastic, and then once the material crosses a certain limit, we normally call it yield stress or yield strength, or UCS, uniaxial compressive strength, or uniaxial tensile strength, whichever mode we are testing the rock or the metal or any other solid material, whether we are testing in tension or whether testing in compression, depending on it will be uniaxial compressive strength or uniaxial tensile strength. But once it crosses that value, okay, the material, we normally say it is going towards plasticity, or it is entered into a plastic behavior. Okay. Now I am going to draw that for you so that you understand what happened when the material crosses that limit. Now I showed you there are 4 different ways it can fall. Now I am going to take the example of ductility. So this is, let's say, again sigma versus epsilon curve in a 1 dimension. Now let's assume this is his yield strength. This is his sigma y. Okay, after that, this is going to depart from elasticity. And in this case, we are assuming this is going to depart in a ductile manner. Always remember that this part is not a straight line, never. But for the simplicity, we are assuming it as a straight line. So what we are assuming is this was supposed to go this way, but this material has yielded. That means some crack or some fractures has developed in that material, and that is that yield strength it crossed. That every material has certain capacity to take the load. So as you know, every human being, not everybody can take all kind of pressure. Okay, so it is similar thing. So different material can take different pressure or different load, but there is not a single material which can take infinite amount of load. The material is going to fail or going to yield. Okay, And once it does, we are interested what will be its behavior. Okay. Now in this case, we are considering it's a ductile behavior. So this is his elastic line. Now you see it is departing. It has departed from that elasticity completely. So according to the, yeah. Anybody has any question? So this is my modulus of elasticity, the slope of this line in the elastic limit. Now, normally in plasticity, okay, I already defined you from here to here is the plasticity. We do not consider a total strain because, as I told you, this is not a straight line. This normally this normally a curve. Normally this is a curve, and after some time it falls. So if I want to follow the curve, I cannot take a big step. Okay, in strain, because I'm going to analyze how this curve is changing. So what we do normally, we take increment of strain. That means we start to take delta epsilon rather than the full epsilon. See, epsilon we are measuring from here. Now we will start to measure from here, let's say some delta. So this much is delta sigma after yield strength. So if this much delta sigma is changed after the yield strength, the strain has increased from this point to this point. So this is my delta epsilon. You can say I'm writing something called T. Delta epsilon T means the total. So this is the increment. Remember that. I'm not taking the total. I'm not counting from here. I'm just what is the increment happened after the yield strength. Now I can conveniently draw a parallel line with this, okay, and then draw is just plain and simple geometry. Okay, so you can see if I draw a parallel line, this is also E, so this much is my delta sigma. Now this has two parts, one is here to here and another is here. So this part we call delta epsilon P, and this small part we call delta epsilon E. That means I can write delta epsilon T is equals to delta epsilon P plus delta epsilon E. Right? Everybody agree with me? Now you are seeing the total strain increment I am dividing into two parts. One is P, we call plastic strain, and this is also called permanent strain. This much strain you have permanently developed in that solid in the form of fractures or in the form of, you know, whatever the cracks it has developed. That means this much strain I will not get it back. So if I return from here, if I release the load, this one will come here, not at zero. So this much strain I have already developed in the body and I will not get it back. Okay. So I think you will study in the next semester thermodynamics. You have to pay very much attention. So,
Sir?
yeah.
Hello, sir. Sir, I didn't get this delta epsilon P plus delta epsilon E.
Okay. So you see this part. This is the total delta epsilon, right? From here to here, the total. Now, when I am drawing a parallel line, this has two parts now. One is this part, which is basically this, same, here to here.
Oh, okay, sir.
Okay,
Got it, sir.
and this
Yes, sir.
small one is elastic part. Now, I am telling you why it is elastic. First I am defining you what is the permanent strain has been developed. And this is the reason the sample is not following this elastic path. Okay. Now, this small part you can see, I can write here, I'll be writing with some another this thing. So delta sigma, I can write E multiplied by delta epsilon E, right? You see this one, if I take this triangle here, then slope of this line is E multiplied by this delta epsilon E will give me the delta sigma. You agree, everybody? So my change of stress, this delta sigma, change of stress is related to elastic strain. Elastic strain, remember that. So whenever stress is changed, either in the positive direction or in the negative direction, it is due to elastic strain. Okay. So the purpose of elastic strain is to change the stress. This is Hooke told us long time ago. Okay, and that is also true in the plastic range. So all the time if stress is changing, it is due to elastic strain only. Because elastic strain and elastic stress or the stress is related to modulus of elasticity. So delta sigma is E into delta epsilon E. Okay, this much clear, everybody? Okay. Now, if for some reason this is a straight line, let's assume, or even since I have made a delta thing, so within this, if I consider this is also has a modulus and we call it ET. This T is basically tangential modulus we call. Now, if this is a tangential modulus, then I can also write ET into delta epsilon T. Do you agree with that? So the change of stress, now I am taking the bigger triangle where this is the delta epsilon T and ET is my tangential modulus. This is called tangential modulus. So this is also true. Now this hypothetically, remember that, I can also write a parameter called H multiplied by delta epsilon P. Although I told you that change of stress occurs due to elastic strain change. But here I am writing a parameter H multiplied by this is just hypothetical equation, it never happens. This H is called hardening parameter. You can write this is called hardening parameter. Okay, this has a particular meaning in plasticity, but this is called hardening parameter. Okay, now, so I have three relationships. Now this is a hypothetical, these two are basically derived from this graph, and this is a hypothetical. Now also I know this, okay, that the total strain increment can be divided into plastic strain increment plus elastic strain increment. Okay, and this is the relationship we can write. Okay, so this is the modulus of elasticity in elastic. This is basically tangent modulus after it yielded, and this is called a hardening parameter. Okay, now if I make them, combine them together, I get a relationship. I will get a relationship. This you can derive in your home also. It become ET. I am not deriving it here, but you can do it. 1 minus E by E plus H. You have to use this relationship. So what you have to do, you have to, somehow omit all these strains strain, and once you remove those strains from these equations, you will get a single equation relating to ET equals to E into 1 minus E by E plus H. Okay, this I want you to do in your home. It's very easy, or it is given in the book also. You can see that later on. Okay, so this is clear. Now, what is the purpose of this plastic strain? What does this permanent strain does to the material? Elastic strain, I made it amply clear. Now this plastic strain, what it does is, it changes the material properties. See, properties in the sense, it changes the elastic property like E. See, that is the equation I have given you, how it has changed. It will change the yield strength, that it used to fail in here, then it will reduce. Now, the purpose of plastic strain is to change the properties of the material. So, you started with the material which has a E, mu, and UCS and yield strength. After it fails, its strength will reduce, its modulus of elasticity will reduce. Okay, so it become much softer material. Okay, so it cannot carry anymore the load it used to carry. Okay, so that's why it will collapse gradually. So this plastic strain, the amount of plastic strain totally controls that how much will be this value. And that's why you have to also account for that plastic strain. But in this class, in this ERM, you will know only up to this much about the plasticity. Now the parameter H, what is its significance? Now I ask you, if the H is greater than 0, okay, if H is greater than 0, then can you tell me whether this ET, is it greater than 0? Okay, let me write there, that way it will be easy. If H is greater than 0, then ET is also greater than 0, right? If H is less than 0, what happened to ET? If H is less than 0, what happened to ET? Okay, this one will become more than 1, so this will be less than 0. And if H is equals to 0, then ET is 0. Okay. So the ET is directly related to that hardening parameter. Now, in other words, this is basically ductile. Okay, when H is greater than 0, you see the ET is greater than 0, it is going up. So it has a value. Now ET less than 0 means it is falling like this. So that is basically brittle or strain softening, we will write. This is strain softening. And this means perfectly plastic. If H is 0 and ET is 0, that means this is a perfectly straight line, right? The slope of this line is 0, that means it's a straight line. This is we call perfectly plastic. Okay. So this is the perfectly plastic material. So by hardening parameter, that's why the hardening parameter is very important, whether it is greater than 0, less than 0 or 0. And this tells us whether the material is ductile, brittle or strain softening or a perfectly plastic material. Okay, so this is what controls the behavior of the material in plasticity. This is, I am telling you, in 1 dimension. This can be extended in 3 dimension also. Okay. Now, let me give you a small problem on this since we have time. Let's see whether you are able to do. This is sigma and epsilon. If you have pen and paper, you start also drawing. Here is the E and here is ET. Now E value is given 25 gigapascal. ET is given 5 gigapascal. Okay, so 1/5. Now I have the stress at point A and this has increased to point B. Okay. Now at point A, the strain was 0.001. This was the strain at point A. This is the yield point. Yield point is 0.0015 and at this point strain is 0.004. Okay, the problem is clear. So at point A, this is elastic part, and in the elastic part, the strain was 0.001. At the yield point, strain is 0.0015. Now the stress has increased from point A to point B, where the strain is 0.004. Now your question is, first you tell me what is the yield strength of this material. What is the yield strength of this material? Sigma.
25 megapascal.
So yield strength will be 25E multiplied by 0.0015. This is the strain, right? It is already given. So whatever it will come, so 25 is the gigapascal. So if you want to change it to megapascal, so you multiply with 3, this much MP. Okay. Second question, you have to tell me what is the elastic and plastic strain between A and B? How much is elastic strain and how much is plastic strain? When it is increased from point A to point B, how much elastic strain has been developed and how much plastic strain has been developed? Who can tell me that? Okay, let me tell you how to do. See, the elastic strain has here two parts. One is from A to yield. Let's say I put it as a Y. So one part is from A to Y. It has gone. So this already delta epsilon E1. This I already know 0.0005. And another one has happened this much. This is the delta epsilon elastic part 2. So this has two parts. Remember that. So now what you have to know is what is the total strain. So total strain is 0.004 minus 0.0015. So how much is that? 0.0. So this is the total strain. Okay. Or the total strain increment from Y to B. Okay. So this is the total. Now you have to find out how much is this stress increment from Y to B. So sigma Y, you already know. So this is the sigma Y here. So how much is here? What is this stress? Can anybody tell me this? I have given you this one. So what is the stress increment from Y to B? Delta sigma from Y to B is 0.0025 multiplied by 5 GPa into 10 to the power 3 MPa. Right? This is the total, this is the stress increment happened from Y to B. Okay. Now this, if this is the stress increment, this is delta epsilon E2 multiplied by 25 into 10 GP. Because this part I am trying to find out, and this is that strain increment into its modulus of elasticity. So this will give me this much. So once you find this is already known. So once you find that, so this plus this is my total elastic strain increment from point A to B. And the plastic will be 0.0025 minus whatever it will give you here. Okay. So everybody understood how to do this problem? Or any confusion anywhere?
No, sir.
Okay. Because you have two different straight line having two different slopes. So you got to change the slope and then there is a strain it is different, so you have to take care of that also. Okay, and rest of the things will be done in your tutorials. So this completes this stress strain relationship chapter. In the next class and the next week, let me tell you what will happen. The first on Thursday we will have a class test, and for about 40-45 minutes we'll see, and then on Friday we will go to a chapter called weight, volume, and mass relationship. Means you will know another properties of material like porosity, permeability, then void ratio, especially the soil type material or the granular material. Okay, what is the properties if the water is interacting with them? Water gets into their pore spaces. Now, I just give you a brief today about just the concept of that. See, so far, whatever I told you, it is just you are assuming there is a material, okay? A solid material and purely bonded and purely solid. But actually, the rock material is made with some grain, and those grains are mostly basically sand, sometimes mud also, and they come with different sizes and different shapes. Basically, now on, I'm going to go into, or the subject matter will go towards basically the rock. Although in between, another chapter will come where again we'll discuss regarding the stresses. But actually, a rock material is made with these grains. And this grain space have lot of pore spaces, means empty spaces. These empty spaces may have water, air, and if you are going towards the petroleum, that may have gas or oil. You know, in here, this is in pore space. Now these grains, we normally call in general grain. These grains are made with either sand or called mud particle, mud. Okay, mud is a very fine particles. Also they have different connotation in geology, the mud and sand. But mud, as a rock engineer, we can assume mud is a very fine particles. And grain means made with basically sand type of particle. So whatever rock we deal with, either mud or sand. And then they have some bonding in between. Bonding, I use some other color. They may have some bonding. And you know what is this bonding? Their bonding is with the calcium carbonate, magnesium oxides, those kind of thing. Because these grains are connected to each other, or by this adhesive material, you may call it. Okay, mostly calcium carbonate type of thing or calcium oxides. You know, next time you see a adhesive packet, you see the composition. You will see they are made with calcium oxide or magnesium oxide. This will be written and some compound of that. or fluoride. Our teeth is strong because of calcium. Our bones are made with a lot of calcium. So that's how these particles are bonded to each other. And then in this pore space, there may be air, there may be water, there may be gas, there may be petroleum products, hydrocarbons. So these are all in pore spaces. Okay? Now the question is, we have to quantify these pore spaces. Like groundwater, the water is flowing through that rock. Now, from where we dug a tube well and we get the water. So that water, how it is flowing? Flowing through these pore spaces. So if you have a pressure difference, let's say there is a rock layer like this, and if you have pressure difference, this is P1 here and this is P2, and if this is greater than this, then water will start to flow in this direction through that pore spaces. The water is flowing through that pore spaces. Okay. So whether it is flowing through the river or through the groundwater table where it is flowing through the rock, they are always flowing from high pressure to low pressure situation. Okay? There must be a pressure difference, and they will be flowing through these pore spaces only. And if the pore spaces are not connected properly to each other, there will be no flow. So if you have to quantify the flow of water or oil or gas, we have to account for the amount of pore spaces and their interconnectivity between them. Okay? So this is a big job of the petroleum engineers and mining engineers and the others. If the water or oil or gas is of concern to us,